Hello and welcome to the Warren County Library. My name is Sandy Roberts and I am your hostess today for Friday S.T.E.A.M. That's where we get together to take science, technology, engineering, art, math, mash them all together, do some fun experiments, explore and learn, and maybe even invent together. And that's what we're going to do today. Last week we started on states of matter, and we're going to continue that theme for the next couple of weeks. Today we are going to learn about liquids. So last week, if you missed last week's talk about solids and the experiments that we did, because we made some sorbet and you might want to go back and learn how to do that, you can find that on our Facebook page or on our YouTube channel, and you can watch it anytime you like. I am next week going to talk about gases, and then we will be talking about non-Newtonian fluids as we finish up. So fun things like plasma and things like oobleck. Sorry, blanked completely on the word. It's one of those days. It's a Friday. I'm ready for the weekend. I hope you are too. Okay, real quick, I'm going to go over what we need in the way of materials before we get started. Then we're going to talk a little bit about the science, and then we'll do our experiments. So that's kind of the way we're going to do it today. Let me go over our materials. So we're going to build two things today. Well, we're going to test one thing. We're going to build one thing. Our first is an experiment, and for that you're going to need, you might remember from last week, my thermos full of ice. This time I made sure I had something with a wide mouth, so I'll be able to get my ice cubes out more easily than I did last week. So I've got ice again for our experiment, and this time we're going to be focusing on, instead of trying to freeze something with the ice, we're going to be focusing on the melting of that ice. So we're going to need some ice. You're going to need a little plate of some sort to work on, and you're going to need salt. Okay? So very similar to last week, but we're going to do something completely different. You're also going to need a little piece of string. The best kind is like cotton thread or cotton string. I'm using kind of a very large string actually so that I can demonstrate on camera. Thinner thread, especially cotton. You don't want polyester if you can avoid it. Natural fibers, burlap, twine, that kind of thing will work. But again, thin and natural fiber. You're going to need a little piece of that. That's for our experiment. As for our invention that we're going to make, we are going to make our own thermometers. And we're going to talk about how liquids expand as they warm up. For that, you're going to need a glass jar. Any size will do. The thinner and taller, the better for this, but this is I think it's a jelly jar. I'm not sure. I already have a hole in the top of mine, but you will need either a screwdriver or an awl to put the hole in your top of your jar. And you may need a hammer to help you with that. Or, if you have a rock, you can go old school on that. If you have a meat tenderizer, that'll work. But something to help you make that hole in the top of your jar. Now, if you have a jar that doesn't have its lid still, that's fine. You're fine. You can use a little bit of plastic wrap and cut a little hole in there. And there are lots of ways to make it work. A little bit of aluminum foil. This is easier, but you can make it work. You're also going to need a straw. I grabbed these from a fast food restaurant. For this one, normally I would say if you have paper straws or metal straws, that's what you want. A paper straw with this is going to break down after a while, and you're going to end up with a very messy thermometer. And a metal straw, it's not clear, and you really need something that's clear or light colored so you can see through it. So this is one of those times that you really do need to use a plastic straw. I know we try to avoid them, but this is one of those times that they're useful. Maybe you've been out to a fast food joint lately or got some takeout. Save those straws, wash them. I wouldn't recommend necessarily reusing them for food, but if you give them a quick wash, they're great for crafts, great for STEM activities. Straws can do a lot of different things. So they're definitely something that you can easily upcycle. But you will need a straw. You'll need a little bit of either some duct tape or masking tape or electrical tape or a little bit of clay or Play-Doh or something like that, because we're going to need to seal up around our hole. I like to go with duct tape because I always have duct tape around, and I don't always have clay around. My kids really like to make little creatures, so the clay always disappears. Last but not least, you're going to need some isopropyl alcohol. I know that this can be a rare commodity sometimes, but it's well worth the sacrifice. It doesn't have to be the 70 or 90%, 50% works just fine. The reason that we don't want water for this is that we really want something that's as reactive as possible. And the higher the alcohol content, the better your thermometer will work. But this is usually pretty inexpensive and is not as useful for sanitation. So sometimes you can find it a little bit easier. But whatever you've got. And that's the other reason that sometimes a thin jar works best, because you're not going to have to use as much alcohol. Okay? And some kind of colorant. I'm using a little bit of liquid watercolor today because we're not going to be using it as food, but food dye works fine. A couple of food coloring drops. Heck, a pinch of Kool-Aid will work in a pinch. I use that word too much. But something to color your liquid you're going to need. So a little bit of watercolor paint, anything that you have like that little ink. But it's going to make it much easier to see the level of your thermometer if you add a little color. Okay. So that's what we need for our supplies. So if you are watching along, maybe mom and dad can go and run and get you supplies if you don't have them ready to go. Quick reminder, I am following along on my cell phone. Oh no, I keep knocking over my paint. I'm following along on my cell phone, so if you have any questions, you feel free to ask, and I will be happy to do my best to answer those questions. Okay, let's get on to the science. This is where I give you a little bit of a presentation, and I know I throw a lot of information at you. But at the end, I have some resources so that you can go and learn more on your own if you're interested. And I will tell you, the states of matter are a really important topic in chemistry and physical sciences. So it's definitely one that you want to take some time to understand if you have any intention of becoming perhaps a scientist or an engineer. So that said, let us head on over to our presentation. I love it when the technology actually works. I'm having a good technology day, and I probably shouldn't say that. Knock on wood. Okay, so talking about liquids. Let's do a quick review of some of the things we talked about last week about atoms, molecules, what matter is, and what the states of matter are, just so we're all on the same page. Okay, so atoms and molecules. Atoms are the building blocks of everything, of all matter. You can kind of think of them like your Lego bricks, okay? You can build them into literally everything, but each Lego brick is a little bit different. It has different qualities, maybe a different color, a different, number of bumps on the top. It's different sizes. So every Lego brick is unique, but each of them together can be built into something bigger and more interesting, perhaps, than that original brick. Atoms are a little bit like that. Each atom defines its own element. Every atom has different qualities, different characteristics. Now, our atoms can be broken down into smaller things, and I kind of glossed over this last week. I thought I'd take the opportunity to hone in on that a little bit. Atoms are actually made up of 3 smaller particles, and each of those, believe it or not, are made up of even tinier things that we're not going to go into today. What you need to know is that there's a nucleus in the center, and it's packed with these things called protons. Protons are positively charged. You could think of positive like if you have a magnet. You might have a magnet where one side has a plus on it and the other has a minus sign on it. And if you try to put the 2 pluses together, they push away because like charges repel. Whereas if you put the negative and positive together, clunk, they'll stick together because opposite charges attract. This is important because those protons in the center of the nucleus, they're all positively charged. So if you tried to make a big ball of them, they would just explode horrifically, okay? So we have neutrons, and they're kind of like the packing peanuts of the atomic world. They basically fit in between our protons and make sure that they don't come too close so they don't blow apart the nucleus. So those are our bigger pieces, our proton and neutrons. In a cloud around the nucleus, organized into kind of layers, from the center where there are the fewest electrons, out and out as you get larger and larger clouds of more and more electrons. What's an electron? Glad you asked. Electrons are negatively charged, itty bitty, super tiny. We've never actually seen one, really fast moving particles. And they're all negatively charged. They're the opposite of the proton, which means they have to be pretty far away from the nucleus or they'll get sucked in. So what people sometimes don't understand from pictures like this is that there's actually a lot of space inside your atoms. And this is pretty amazing. We'll talk about more about why it's amazing next week. But what you need to know is that you have your neutrons and protons in the nucleus and electrons whizzing around outside. Electrons are a little bit like adventurers, especially when they're way far out on the outer reaches. They sometimes want to go exploring. And it's very easy for one atom to grab electrons off of another atom sometimes. And sometimes atoms even share electrons, and they just kind of cozy up and they share that electron. Like if maybe you've curled up with your mom or dad or a friend around a blanket, atoms kind of do the same thing. The whole point of this is when atoms share their electrons or steal electrons from one another, they form bonds, and you get atoms that come together. When those atoms come together, we call them molecules, and molecules make compounds, and compounds are most of the chemicals in our world. Okay? Everything that we eat, everything that we drink, everything that we are, pretty much all molecular compounds. Okay? So there are about 120 different elements, and when you combine them, you can make literally millions of different molecules. So if you think about the alphabet is what? 26 letters, and we get a lot of words out of it. Now imagine you had 120 letters to work with. You can make a lot of different things. So molecules, like I said, they just bind together when we share electrons between atoms. And even those smaller molecules can even bond together and work together and become macromolecules. And those are things like when we talk about carbohydrates. Maybe your parents talk about limiting their carbs. Carbohydrates are a macromolecule that we eat because they're delicious. All right. So basically, once you combine your atoms, now they're going to have different qualities. Again, going back to our Legos, when you stack different Legos together, you can make rounded shape. You can make tall towers. You can make triangles. So the individual elements, when combined, make something completely new. And that's what we see with elements and atoms versus molecules and compounds. For example, I always use this example. If you take the very reactive explosive metal sodium and mix it with the poisonous gas chlorine, you know what you get? Delicious salt for your potato chips. Chemistry's cool. Okay, that's a review of atoms and molecules. So what is matter? Well, matter is just anything made up of atoms and molecules. I know it's a little circular there, but you get the idea. Matter is one of the important things in the universe. Pretty much the universe is matter and energy. And matter can become energy, and there has to be a balance at all times, okay? And we can take energy and we can make new matter. That's how you grow. You eat stuff, you get energy, you make new you. So matter is defined as anything that takes up space, okay? So it has a volume and has mass, which basically means does it weigh something? Does it have molecules into it? Mass is just the amount of matter in an object. Volume is just the amount of space that it takes up, okay? Every piece of matter takes up space. And if you've ever gotten into a bathtub that's really, really full or tried to put ice into a glass of soda when it was really close to the top, you have seen displacement of volume in action because those ice cubes take up space and they're going to push the liquid out of the way. Okay? And if you've ever tried to carry, I like to use the example of if I gave you a bag of feathers and an equally sized bag of rocks and I told you you had to carry one all day, you're probably going to choose the feathers because they have less mass in the same volume. So they're less dense. Density is really important, especially as we talk about liquids today, because density has a lot to do with solutions, which we're going to get to. Basically, density just describes how much space an object takes up and how much stuff is in that space. So in my example of the feathers and the rocks, you could put 100 feathers in that bag and 100 rocks in that bag. The rocks are still going to be more dense. They're just going to have more mass in that same space. So objects that are really heavy and compact tend to be really dense. And you can see that in this picture. Here's something that's very dense on one side and a lot less dense on the other. In general, liquids tend to be less dense than solids. Okay? And gases are even less dense than liquids. And this has a lot of effects on things, right? Less mass means gravity is going to affect it more. It's going to be harder to lift, basically. So this very simple of density can really, really affect how matter acts. Okay, speaking of matter, states of matter. States of matter, we typically think of solid, liquid, gas, but those are just 3 common forms here on Earth, and we're discovering that that may be just the tip of the iceberg. We know of at least 5 states of matter present in this universe, in our local universe. So solids, liquid, gases, plasma, and Bose-Einstein condensates. You may also talk about non-Newtonian fluids. So there are all kinds of different states of matter. We mostly need to worry about solids, liquid, gas. In that 4th class, we'll talk about some of those other crazy ones. Things like plasma, actually, we're learning to use right here on Earth. So the change from one state of matter to the other is a physical reaction, okay? A physical change, much different than a chemical change, okay? And we're not doing any kind of, chemical reactions today. So if you put baking soda in vinegar, that's a chemical reaction. In this case, we're just talking about a physical change. Usually, we go from a solid, which gets the influx of energy in the form of heat, and when it hits its melting point, right, it's going to become a liquid. So an ice cube melting in the sun eventually absorbs enough heat that it starts to melt, hits its melting point. That liquid, when it gets really, really hot, it will start to evaporate, okay? That's its evaporation point, its boiling point. And again, that's an influx of energy usually. So you can think of it as water. You can melt some ice cubes, you can boil the ice cubes, you can make some water vapor. But you can go in the opposite direction too. When that water vapor, floats way up into the sky, for example, it gets cold up there and it's going to condense. What's interesting is that the boiling point and the condensation point are basically the same temperature. It's kind of that magic point where everything changes. So that water vapor, okay, that gas is going to condense into droplets of liquid. And this is why it rains, my friends. So that liquid then, when it gets colder and colder and colder, it's going to hit its freezing point. Again, freezing point, melting point, same temperature. 2 sides of the same coin. When it hits that freezing point, it's going to become a solid. And that's really all you need to know about physical states. Now, all of this can be affected by some outside influences. For example, if you have changes in pressure, it can affect boiling points and freezing points. This is why sometimes you'll see in cookbooks that there will be separate instructions for baking or cooking if you're at a high elevation, which basically means if you're in Colorado, way up in the mountains, you have to take into account the fact that the pressure on you is different than someone who's down on sea level, in a bay in California, okay? And that will actually affect the boiling point of liquids and can affect your cooking, which is pretty cool if you think about it. So pressure is one thing that can change it. The other is if it's not a pure substance, okay? And that's why we talked about density, and that's why we're going to talk about solutions. Because if you have something mixed into your liquid, okay, it can dramatically affect its boiling and freezing points. So, moving on to liquids. All right, basically liquids are found somewhere between a solid and a gas. You've probably encountered liquids before. We tend to think of things like water and juice, but honey is a liquid too. So blood is a liquid, okay? There are lots of liquids out there is my point. Liquids are pretty cool because they fill the shape of their container, right? Can you see that? That's very different than solids. Solids don't do that. They have a rigid structure. But because liquids are less dense, because they're less bound to the other molecules in that material, because they're more high energy, they tend to move around a little bit. So you can kind of see this in this graphic, where solid is really packed in, liquid a little less, and gases, they're just all over the place. So another trait of liquids is that you can't really compress it. Have you ever had a glass of water and tried to press down on it? That doesn't work. Don't try to do that. That's not going to work. To a little bit it will. Like you do put pressure on the pool when you jump into the water, but you can compress a solid way easier than you can compress a liquid. There are some exceptions, right? For example, making dry ice. Dry ice is fun, but that's a discussion for another day. But dry ice is an example where if you change the pressure and compress that gas into a liquid and then into a solid, you can make it work, but you have to use a lot of energy to make it happen. Now, liquids have a lot of what we call cohesion. So this is basically where those molecules, they're interacting because they're all floating around, they're doing their thing, they're checking stuff out, they're very social. Solids are locked together. They can't really do that unless you really force them apart, usually by melting them. Gases are bouncing everywhere. They want nothing to do with each other. But liquids are somewhere in the middle. They interact, and because of that, sometimes the molecules get sticky with one another. So, experiment number 1 for the day. And I'm not going to demonstrate this, but if you get yourself a nice penny and a little bit of water and a dropper, you can drop water onto that penny and you will see that rounded shape form, and that is because of cohesion. Those water molecules are trying to stick together in the most efficient way that they can, and that's usually a rounded shape. So it's really fun to see how many droplets of water you can get to fit on the face of a penny. Now, once you're done with that, and you've tallied your number of drops, here's a second experiment you can do. Get some dish soap, oil, rubbing alcohol, milk, and see how many drops you can get of each of those on your penny. Because it's going to be different. Different densities, different viscosities, different solutions of different liquids will have different levels of cohesion because they're different molecules floating around in there. Second experiment you can do, clean your penny, coat it with oil, dish detergent, rubbing alcohol, and see how many droplets of water you can get onto it. This will affect surface tension. And what that basically means is that certain liquids can actually break up that cohesion in other liquids and break that surface tension, that beautiful kind of bubble that we have along the top that's holding everything in. So some things will actually break that and you won't be able to form that dome of liquid on the penny. So I invite you to experiment with that, and I'd love to hear what your results are. For those math geeks out there, get yourself a dime, a penny, a nickel, a quarter, clean them all the same. Measure each one, circumference across, get an idea of the surface area. If you know that formula, go ahead and calculate it. And then see how many drops of water you can get on each of the different coins. Then ask yourself, is the number of drops I can get onto the coin directly related to how much surface area I have? Like, if my quarter is twice the size of my penny, can I get twice as many drops? Or is there something else going on? So I'll let you guys crunch those numbers. So that's your first kind of fun that you can have with liquids today. Moving on, solutions. This is a big, exciting part about liquids. And if you ever had a soda, if you've ever had iced tea, you've enjoyed a lovely solution, okay? All a solution is when you have different types of molecules dissolved into a liquid. So, for example, honey is a solution of sugar and water and other molecules. And those other molecules can get pretty complex. But solutions are just a group of molecules. They're mixed. Here's the thing about solutions. And you might remember from last week when we talked about solids, there are 2 types of mixtures that you can get. One is homogeneous, and that's this example on the first side here, the left side. Everything is mixed exactly evenly. Everything is spread out exactly the same. Heterogeneous mixtures, though, it's not. Like if you make yourself a salad, you don't carefully place every grape tomato in exactly the same spot across the whole salad, right? I mean, you might. It's your salad, whatever you want. But most of us are just going to toss them in and let them fall where they fall. With solutions, though, they're all homogeneous because given a little time, everything will distribute itself equally throughout the solution. And this brings us to solubility. Any solution is basically 2 things mixed together, okay? You have your solvent, which is what everything is dissolved into, and your solute, which is what's being dissolved in. So, for example, if you have a glass of water and you put a teaspoon of sugar in it, the water is the solvent, the sugar is your solute. Now, there's only so much solute that you can put into any given solvent. And that's what we call our solubility. Some solutes are more soluble than other solutes. For example, sugar, very soluble. Iron filings, not so much. Okay? So that makes certain solutes, like sugar and salt, very desirable for making solutions. But there's only so much you can put in there. I'm hoping in the new year to do a edible inventions class for the library, and we will get all into solubility and saturation. Now, concentration just refers to how much solute you've put in something. So you can see here in the picture, a concentrated solution has a lot, a dilute solution has a very little. And you could think of it like if you have a glass of water and you put 1 drop of food color in there, you're going to see a pretty maybe blue color. You put the whole bottle of food color in there, it's going to be really dark. Okay? One is very concentrated, one is very dilute. And sometimes that makes a big difference. Okay? With certain cooking, for example, or if you're making iced tea, you may not want the strongest tea. So concentration does make a difference in a lot of different ways, both in how that liquid is going to react and how, in the case of cooking, it'll taste. Okay. That was a lot to throw at you. I hope that you're still sticking in there. And again, if you've got questions, I'm watching. If you want to learn more, I recommend Chem for Kids. It's a website I've used for many years, and I used it a lot in my middle school classrooms. So it's just chemforkids.com. They have great sections on all kinds of chemistry. They also have a physics site and a bio site, I believe. But they take you through kind of step by step, and I used that as my reference material for this presentation. So that's a really good site if you like to read. If you like to watch videos, Crash Course Kids has a whole playlist on matter, atoms, molecules, everything you could want to know. And they're really fun, short videos. They've got good music, a cool host. I also use those a lot in my middle school classroom. I love Crash Course Kids. And of course, check the library for books. We have lots of science books in our collection. Just go to warrenlib.org, look through our catalog, pick some books. We have digital offerings on Hoopla too. And if you're really not sure, call for a grab and go and just say, I want books all about states of matter. And they'll find you all kinds of stuff on states of matter. They'll find you videos, they'll find you books, whatever you want. Okay, that's it with the presentation. Time to do some experiments. Oops, I whacked my mic, I'm sorry. Okay, let's do our experiments. I'm gonna switch over to my document camera. Here we go. All right. So, I'm still watching along. Our first experiment, we're gonna use our ice. And I apologize that my mat is a little, well, I made I made lollipops the other day for a different class, and I warped my mat because it got hot. I guess I'll have to heat it and press it back out again. Anyway, so hopefully this will work nicely. I'm going to take one of my ice cubes, put it in my tray here, and we're going to play with freezing melting points. Now, you may remember last week we talked about how using salt with our ice and water would lower the freezing point. And by lowering that freezing point, we could get the liquid inside our bag for our sorbet to freeze, right? Even though it was still, liquid water around it. But salt is one of those things that can affect freezing temperature. Remember how I said when you make a solution sometimes, it will affect the characteristics of that liquid? Well, that's exactly what's happening. Salt water freezes at a lower temperature than regular old tap water. And that's why we use salt in the wintertime to dissolve ice. Well, you can also do a fun magic trick with your friends. So, the next time you get together with your family, or if you have a homeschooling pod, or a couple of trusted friends that you're visiting with, get out some ice, give everybody a piece of string, and challenge them to pick up the ice using the string, can't touch with your hands, okay? And they're going to do a whole lot of this. You can't touch it, can you get it? And come out with a bit of salt. And I know, see, it's not level, so that's what's calling it. And you're going to sprinkle your salt right on there. What's going to happen if you let it sit for just a little bit is your ice is going to start to melt. Okay, that salt is going to melt it. And as it melts, and you don't want, I put probably too much salt on here. It takes them off. As it melts, it's going to change into a liquid, but that freezing temperature is rapidly going to come back up, and it should, and this is where a thinner piece of thread is going to work better. I put way too much salt on this. You really want to sprinkle, not dump like I did. Oh no. Let's see if I can get it to work. I'm gonna have to turn it over and do the other side. If you let it sit for a little bit, yep, okay. I'm gonna turn it because I dumped way too much salt on there. Try this again. If at first you don't succeed, little bit of salt, Sandy, little bit, okay? And you hold it there. What should happen is your ice will melt just a bit and then refreeze, and that will capture your string on the ice or in the ice. And when that happens, you should be able to lift your ice. Oh, I'm having trouble. I don't have the best string because I chose a wide string so you could see it. And I think I should have just gone with thread. Probably should have just gone with thread. Nope. This is what happens when I change things up last minute. All right, well, I will leave that for you guys to experiment with and see if you, I'm going to leave this and let it sit while we chat about our other thing and see if we can get it to work. I'm going to put a little more salt on there. Whoop, that's a lot. I keep on putting too much salt on there. I'm going to let this sit and we'll see if we can get that to work, okay? I think I just have a very thick string and it's not absorbing as well. So I'm going to let that sit. You can try it too at home. Another fun thing to do, by the way, in the winter is to get like big pieces of ice from outside and sprinkle salt and food coloring on it and let it kind of melt and then press paper into the food coloring and you get some really wild ice prints. Okay, I'm going to put that aside for now and I'm going to show you how to make our thermometer while that does its thing. So here is my jar. And as you can see, I've already put a nice hole in the center. You can use a nail, a screwdriver, and all. I just used a screwdriver and a hammer, and I just plunked a hole in there. The important thing is you want to make sure the hole is large enough for your straw. So I'm just going to double check that it is. And you can see I've got a white straw, so it's fairly easy to see through. The clearer, the better. Yeah, it's a good size. Now you notice I'm not putting the bendy part. Okay, I'm putting the straight part right on into my jar, and I'm just going to use a little bit of tape, but you could use clay, Play-Doh, hot glue, whatever you want. The goal is just to make sure we seal up that hole really well. Mine is pretty tightly sealed. And you'll notice I did not go all the way to the bottom. I do not want to go all the way to the bottom of my jar. I want to give it some space so that the liquid can flow in. Now when I'm doing tape like this, I like to rip it like halfway, and that kind of gives me the ability to form it around my straw. There we go. You don't have to get fancy about it. You can, if you want to make it look beautiful, cover the whole top with duct tape, make it look cool. That's up to you. Just leave the sides of the jar nice and clear. I'm going to remove this, and I'm going to get my alcohol, isopropyl alcohol, and I'm going to fill my jar about 1/3 of the way. Okay, I don't need it really high. And I'm just going to add a little bit of food coloring or liquid watercolor or whatever you've got to it. Isn't that always fun? Now you notice, did you see that? Let me see if I can get a close-up. I'm going to add more. I'm going to make it darker than I might normally. We're making a solution here, right? I'm adding, in this case, one liquid to another, but this liquid is carrying a pigment, and that pigment is our solute. The water is our solvent, and you can see as it goes from not being dissolved to spreading out and becoming homogeneous. It goes from heterogeneous to homogeneous, and that's part of the beauty of liquids as they become solutions. So there we go. I'm going to add even a little bit more. I want it kind of on a darker side for this. That'll make it easier to see through the straw. And you'll have to vary how much you use based on, what you're using. I will say, now as far as the alcohol goes, the reason we're using alcohol is because it's a little more reactive to temperature. Remember how I said that different liquids have different properties? Well, one of the different properties is different melting points and boiling points. Rubbing alcohol evaporates more easily. It has a lower boiling point than water. We want it to really react to changes in heat as much as possible. That makes for a good thermometer. So 50% isopropyl alcohol will work. the more alcohol, the less water, which is what the percentage refers to. This is basically saying it's 50% alcohol, 50% water. So if you have 99% alcohol, that's going to be even more reactive to temperature changes. So that would be desirable. However, it's also better for sanitation, so you may not want to share it. All right, so I've got my water in there, or my alcohol in there, my food coloring. I'm just going to go ahead and add my straw. Okay, this works pretty simply. Let's see if I can if I can do this. When my alcohol gets warm, okay, it's going to rise because, and this is a really important aspect, is that when energy gets into our liquid, those molecules are going to move around more. As they move around more, they're going to bounce off each other. They're going to start to spread out. This is a fairly small change as liquids warm up, but it's the reason why when enough energy gets into the liquid, those molecules are like, nope, I got to break free, and they become a gas because they just want to move away from one another so much. But we can capture that happening in our thermometer because as the liquid gets warmer, it's going to expand just a little bit. And when it does that, you will see the level of our liquid rise in the straw. Okay? This is a little harder on a winter's day or a fall day than it is on a summer's day. But if you put this in the sun, you will absolutely see that level rise inside your straw. You can even just hold it in your hands for a while. This is another reason why I said the more narrow a jar you can get, the better off you're going to be. So that's all you have to do to make a thermometer. Do not close this part off. If you close that part off, remember how we talked about putting pressure on our liquids? Well, that's what you would be doing. You have to leave that open to the air so that it can rise and fall as it needs to. So there you go. That's your simple thermometer. If you want to learn to make other weather items, this book has lots of ideas in it. You can get it from the library. We have lots of books on weather and constructing your own weather equipment. So check that out too. That's another really fun thing to do, making rain gauges, barometers, etc. All right, let's do a quick check on my ice. Well, it lifted part of it, but it didn't lift the whole thing. So I should have just gone with my usual and used thread and not try and change it up last minute. But I encourage you to give this experiment a shot, and if you succeed, I want to see pictures. Use the hashtag #WarrenLibs so that I get to see your success. All right, coming back over here. Well, that is all our time. Ooh, that is more than our time. I need to head off to my next class. Thank you so much for joining me for Friday STEAM. My name is Sandy Roberts. I'm the Makerspace Coordinator for the Warren County Library System. Please make sure you check out our website for all the fun events that we have going on. Check out our digital resources, our grab-and-go bags, and our Beyond Books loans. You can borrow a metal detector, binoculars, all kinds of really fun stuff. Until next time, stay safe, stay healthy, have a wonderful weekend. Take care. Oops.